Development Association. So, to start with, who is the Nickel Institute? Who are we? So, nickel is a key element in more than 75% of all stainless steel produced delivered materials, and it's actually having outstanding physical and mechanical properties, and that makes stainless steel such an attractive and easy and durable solution. So the Nickel Institute is a non-profit, that's important, global association of the leading primary nickel producers. Our mission actually is to promote and to support the proper use of nickel in appropriate application. And this is as well why we are doing tonight's webinar on the topic that Gary will present afterwards. The Nickel Institute as well grows and supports the markets for new and existing nickel applications, including, of course, stainless steel. And importantly, we promote sound science, risk management, and socio-economic benefits as the basis for governments and public policy and regulators. So we are divided into 4 divisions, or we are working out of 4 divisions. Gary and we are in the market development team. So we grow and we try to defend as much as possible the markets for new and existing nickel applications. Important is as well the science behind all this. So the science department, they undertake the science for the relevant human health and environment issues. They perform risk assessments as well for governments and other associations. Then the health and environment public policy team, they promote then the sound science. They communicate with governments and relevant associations. They do the risk management, they do socio-economic benefits, and they promote all this. As such, at the end, we have the communications team. They are very important to build the nickel brand and as well to inform with the documents, papers, and I will come to that as well, brochures to the relative associations and regulators. So, why is it going back? Voila. Where are we located? So our headquarters is sitting in Toronto, Canada. Then we have the science division, NIPERA, that is in the US, sitting in Durham, North Carolina. Anything that goes into health, environment, public policies, that is located in Brussels. That's the Europe headquarters. Then we have 2 non-profit incorporated offices in Tokyo and 1 in China, and 2 representative offices, 1 in Singapore and 1 in Brisbane. Who are our members? As I mentioned in the beginning, these are the leading nickel mining companies. So this is who is contributing to the financial parts of the Nickel Institute so that we can do this free of charge webinars as one you will hear tonight. Important for everyone, and we try to make this, or we do it already for many years, promote this technical help. You go onto our webpage, the nickelinstitute.org, and you will see immediately this big yellow box, technical help. You click on it, you will go to a short registration process, and you can put in any technical questions you have around nickel, stainless steel, and so on, and you will get free of charge information within 24, maximum 48 hours back from one of our experts. This is worldwide, take use of it, and that would be great for everyone to be used. Now I would like to show you a quick movie about nickel.
What is nickel? For starters, it's the 5th most common element found on our planet. It's produced in more than 25 countries. And it's used in hundreds of thousands of everyday products. Without it, our modern world wouldn't function. But to most people, it's a complete unknown. So what is it that makes this extraordinary metal so special? It's resilient, strong, resistant to corrosion, highly ductile, with a super high melting point. Not to mention its useful magnetic and chemical properties. All in all, a pretty handy element. But that's not everything. More than 2/3 of nickel produced is used to make stainless steel. This amazing alloy is used in everything from spoons to spaceships. Pretty impressive stuff. Nickel improves the strength of stainless steel and helps it cope with extreme temperatures and corrosive environments while making it easy to use. It's the perfect partner for engineering and construction projects. The metal is also a key component in modern batteries, enhancing their energy density and helping to power the future of transportation. Nickel-containing materials are used to meet the demanding conditions of the oil and gas industries and other methods of power generation, including renewable energy. And those anti-corrosive properties help provide invaluable protection for a huge range of maritime applications. Nickel helps ensure the delivery of clean water. Being resistant to damage from earthquakes or extreme weather, the lifespan of pipes is extended and leakage is reduced. And what about recycling? Nickel is one of the most efficient materials for reuse. Almost 70% of nickel is currently recycled again and again, contributing to a sustainable, circular economy. Nickel, the hidden metal that makes the modern world work, now and in the future. Pretty extraordinary, really.
Yeah, hope you enjoyed this short movie. Now I would like to come to our presenter and as well the technical expert of today's webinar. Gary is the technical manager for the Nickel Institute and is sitting in Toronto, Canada. Pretty early morning. Thanks for getting up that early, Gary. Gary, he has worked in the stainless steel and nickel alloy industry for the past 45 years. The last 21 with the Nickel Institute. Welding has always been a major interest, as often welding is the weakest link in fabrication. He has worked with many different end-use industries and with fabricators to ensure they have access to proper welding information. He is actively involved with many professional societies, including the American Welding Society, and he's an active contributor to their welding forum. He has made many presentations in India on all aspects of use of stainless steel and nickel alloys. And now I would like to hand over to Gary to start the webinar. Thank you.
Thanks a lot. Yes, and I'm going to reclaim the host so I can then share it with Gary. Gary, you've been made the host and you should be able to share your screen now.
Yep, okay. Let's get this one up here. Hopefully everybody can see the screen now, can they? Oh, sorry, no. Just hang on.
Not yet.
Sorry. Bear with me. I was doing it wrong here. Now I think you can see the screen, can you not?
Yes, we can. Yes, we can.
Yeah, okay. Well, first of all, a big thank you to Dr. Krishnan and Mr. Nimesh for having me here today. It is one of my favorite topics is the welding of nickel alloys, and even the copper nickel alloys come into that. And of course, I would rather be there in Mumbai with you people. I always enjoy coming to India, and we have learned during this time of COVID that the second best way of doing it is by webinars such as this. So
Yeah.
please, please feel free to ask questions through, I guess, the chat line there, and we'll try to answer them at the end. Okay, so we're going to talk, I'm going to do a short introduction on nickel and copper nickel alloys, so we're all on the same page related to what kind of materials we're talking about. A section on before you weld, because if you don't have the material right, the welder, the welding engineer isn't going to be able to have it welded properly. And then of course, the bulk of the session is on the welding of these materials. Couple of slides on post-fabrication inspection and cleaning, and we have some very good references that you can look at, and a short summary, and then a time for questions. So one of the issues with nickel alloys is that they are used in conditions that are very severe, highly corrosive, maybe containing toxic chemicals or explosive chemicals, flammable chemicals, and especially used at higher temperatures where the stainless steels don't work. So we really need to take extra precautions to ensure there's no issues with them throughout their service life. And that's for protection of the people in the plant, people in the surrounding communities, and of course the environment. Now, this is not so much true for copper nickel alloys. They're used in more benign situations. We'll come into that shortly, but many of the nickel alloys are used in very severe environments. And they're expensive materials, so we want to do it right the first time. Now, I saw in your in January 30th, you're going to have a wonderful session, and it is very important, as the presenter talked about, that there be teamwork. It's the welding engineer, the welder, the welding foreman. It's a team that has to all get it right, and each has their own competence, and they each have to work together to make sure it is done right. So first of all, what is a nickel alloy? It may sound like a not too intelligent question, but the definition has changed. So today, the ASTM definition of a nickel alloy is an alloy with more nickel than any other element. However, previously, the definition was that the iron content of the alloy had to be less than 50% and more nickel than any other element than iron. And that was then called a nickel alloy. So, and the UNS number system followed this earlier definition. So let's take an example of the first one there, the 904L. The UNS number begins with an N because that was a nickel alloy, or considered one earlier. It has 48% iron, 25% nickel. Previously, ASTM called it a nickel alloy. It was found in the ASTM-B specifications and ASME-SB specifications. But today, ASTM is calling it a stainless steel. Same thing is true for alloy 800. And we think of alloy 800 really as a nickel alloy. It is typically produced by nickel alloy producers. But today, ASTM considers it a stainless steel. However, an alloy like 825, because there is actually more nickel than there is iron, is still considered to be a nickel alloy. Now, what is partly confusing here too is ASME has not been quick to make those changes in their codes. So ASTM has retained the original standard. So for example, both 904L and alloy 800 are in both the ASTM-B and the ASTM-A specifications. So there's a duality there. which eventually will get eliminated. They eventually will take it out of the B specifications. But in the meantime, it can be very confusing for people. So there are two main classifications of nickel alloys, and this is really very important when it comes to using and welding these materials. Many of the nickel alloys contain chromium, just like a stainless steel, and a number of them do not contain any significant chromium content. So for example, the alloy 800, we call nickel chrome iron because there's a fair amount of iron there. 600, we know it often as trade names like Inconel 600, but it's a generic. Alloy 800 is nickel chrome. There's a little bit of iron there, but we call them nickel chrome alloys. Nickel chrome iron molybdenum alloys like 825, and nickel chrome moly alloys such as the 625, and the many types of C alloys. And just like stainless steels, these grades with the chromium on it form a passive oxide film on the surface. The molybdenum and certain other alloys help to strengthen that passive oxide film. They're suitable in oxidizing to moderately reducing corrosion environments. The ones that don't contain chromium are alloys like the B family, which are only nickel and molybdenum in it. The nickel copper alloys, we know them as most commonly as Manel 400. Manel is actually a trade name, so alloy 400. And then commercially pure nickel, which is 99% minimum nickel content. Alloy 200 is an example of that. They rely on their bulk composition for their corrosion resistance and are suitable for moderately to strongly reducing conditions. They are absolutely terrible in oxidizing conditions. Because they don't have chromium content, don't form a passive film, they are not good in oxidizing conditions. Now you might say, well, what is oxidizing and reducing? And I'll come to that very shortly. But I'll just briefly introduce the nickel, the copper nickel alloys and how they relate to that alloy 400. 90-10 copper nickel is roughly 90 copper, 10 nickel, and 70-30 is 70 copper, 30 nickel there. And they are commonly used alloys in seawater and other chloride salt applications. Okay, now there is also another family of nickel alloys which are called age hardenable alloys or precipitation hardenable alloys. And they're like the 17.4 pH of the stainless steels. They harden, but through a precipitation mechanism. It isn't a quench and temper kind of hardening operation. You heat it up to a certain temperature, the precipitates form that makes it strong and hard. Most of them are not welded because the heat from welding changes their properties. The heat affected zone, you heat it up to a temperature where the precipitates involved. When they do need to be welded, special precautions need to be taken. I will not be dealing with those alloys here. And just an idea of the strength levels, this is for the nickel alloys according to ASTM, and in red at the bottom, I compare them to 304. Many of the nickel alloys are just slightly stronger than the standard 304 material. The B alloy, B2 alloy, for example, is 50% stronger in yield strength. Most of them are only slightly stronger, and a few of them, such as the alloy 400 and the commercially pure nickel, are actually a little weaker than the 304 material. You can see from the right-hand column, the percent elongation is all quite high. They are very ductile materials. When it comes to copper nickel, they are both in the fully annealed condition weaker than a 304 material, and just like the alloy 400, they're even weaker than that. the Manel K500, or the precipitation hardening grade or age hardening grade, is a lot stronger. You can see the yield strength is a lot higher than either the stainless steels or the copper nickel alloys, or the pure nickel copper alloy. Because of that, the elongation, really indicative of the ductility of it, is lower, still reasonable, but not as good as the annealed materials. Now, there is a copper nickel grade, a 9010 grade, that is work hardening, that has a much higher strength. It isn't used a lot, and because it is work hardened to get the higher strength, again, when you weld it, you're going to affect that property, at least in the heat affected zone. And so it is commonly not welded. It is used more for springs and certain other equipment, bar material perhaps. So I have 2 slides on corrosion. The idea is that you really should understand where you use these chromium containing nickel alloys versus the non-chromium containing ones. So we talked about oxidizing and reducing before. Some of the chemicals that are oxidizing include things like chromic acid, nitric acid, concentrated sulfuric acid, oxidizing salts as we get weaker in the oxidizing nature. On strongly reducing, we have the halogen acids, hydrochloric, hydrofluoric, hydrobromic are strongly reducing, caustic, sodium hydroxide, potassium hydroxide, middle concentration sulfuric. And as we get to dilute sulfuric, it's getting more weaker on the reducing area, but still reducing there. And of course, as you can imagine, the chemicals that are strongly oxidizing, you want to have a passive surface film. For stainless steel nickel alloys, you want the chromium in there, but titanium falls into that category. It forms a titanium oxide protective layer. And then the stainless steel and nickel alloys that contain chromium do well in the strongly oxidizing conditions. In strongly reducing conditions, those alloys don't do very well at all. Zirconium, the nickel molybdenum B alloys, the pure nickel, the nickel copper alloys, and the copper nickels all work well in reducing conditions there. Now, in the middle between this Y, the arms of the Y, we have an area that is, I call it the middle ground. It can be oxidizing environments with reducing impurities, or reducing environments with oxidizing impurities. And this is where a lot of the nickel alloys fall, things like the C-type alloys, C276, C22, the 625, and we get into the high alloyed stainless steels, 6-moly stainless steels, 904L, work in slightly lesser conditions, and then 316L, 317L fall into a even lower level, but still they can tolerate some oxidizing conditions. They have that passive film, but they have elements like molybdenum that give it corrosion resistance to reducing conditions. Now, the next section, before you weld. And this is something that is, again, we talk about teamwork. Of course, your purchasing people will probably be the ones that are actually ordering the material. They will have to know how to order it. Now, if you're an end user, somebody who's using it, you probably know exactly how it's going to be used, but you may not know exactly how to order it. The purchasing person usually doesn't know so much, but it's the corrosion engineer in the plant, perhaps somebody who's a specialist who knows exactly what is needed. So typically, nickel alloys require higher purity alloying additions in stainless steels. So not everybody can easily make them. More important, they often need additional refining, and I'll come back into what that exactly means, but secondary refining. And unfortunately, the US composition doesn't indicate anything about it. Even ASTM, ASME specifications do not make it clear whether secondary refining should be mandatory or not. And they don't even talk about the primary refining in any degree. So it's really up to the purchaser to indicate if he wants a specific refining method and including a secondary refining of it. And I just quote a little bit of ASTM B906 there, which is for a general requirement for nickel and nickel alloy plate, that it really tells you nothing, to be honest. So what is primary refining? Well, electric arc furnace is typically where you melt the material. You take the raw elements and you melt it in the electric arc furnace. A foundry, somebody who does castings, they typically only have an electric arc furnace. There's a few that do have other refining methods, the AOD and VOD, but most of them only have an electric arc furnace, and it can only do a little refining. You really need high quality ingredients to go if you don't have any other refining other than the electric arc furnace. Most nickel alloy producers will have AOD. That's the same thing that 90% of the stainless steel producers have, argon oxygen decarburization, very efficient in refining, cleaning up the material. Or a few people have vacuum oxygen decarburization, does the same thing as the AOD, but slightly different methods. Secondary methods of refining, once you've done the primary refining, are electroslag remelting, vacuum induction melting, and vacuum arc remelting. The latter two methods are more typically used on aerospace alloys rather than the corrosion-resistant alloys. The vast majority of them are secondarily refined in the electroslag ESR machine. So now in the past, the major producers of, let's say, the C-type alloys, C276, C22, they always did an ESR treatment on the material. However, and you can think of the names like Haynes and Special Metals, or what used to be Inco Alloys, and VDM and Allegheny in the United States. I'm more familiar with those ones. They always did ESR on the C-type alloys. But a number of producers around the world have said, well, that's an expensive operation. The ASTM spec doesn't require it. So to be more competitive, they skipped the secondary refining method. Since that time, and that was probably 25, 30 years ago that started, there have been a number of corrosion failures of components that have been blamed on the lack of secondary refining. Now, in 90% of the cases, there haven't been a problem, but in maybe 10% there is. So it's not always clear when you have to have it secondary refining, ESR'd, or when you can get away without it. And there's a big cost premium. It's in the area of like $2 a kilo to do an ESR remelt on a material. So not inexpensive. And on top of that, we do want to make sure the material is in the best possible condition. And again, ASTM specification for, if you just order it to the standard one for plate, it doesn't require any sort of acceptance test. So many chemical producers, and I'll just name like people like Dow and BASF, they will specify an acceptance test for the material. The acceptance test, for example, for C types and 625 is a G28A test to be done. However, there is no acceptance criteria given in that ASTM spec. So the end user really has to come up with their own criteria. And I'll just mention that MTI, the Materials Technology Institute of the chemical process industry, has had one project. We're in the middle of a second project to define what are typical values for good quality materials of C type. They already did the 625 type. So that acceptance criteria is really critical there. There is some information on the internet about that, and values are given there. When it comes to the B-type alloys, there is no standardized test there. Each producer tends to have their own test that they will check it against. But again, if you really want to make sure you're getting the right quality material, you have to specify the test and specify the acceptance criteria. And just as a comment, things like the nickel copper alloy 400 and the commercially pure nickel 200, they are simple alloys. They don't need to have a corrosion test. And some of us like micrographs with bad phases that are in there. And I just show you a picture of C276 and B alloy that has that have been badly heat treated and have lots of grain boundary precipitates. It's not carbides there. There may be some carbides there, but there are other phases. They're mu phase for the C alloy and a nickel molybdenum phase for the B alloy. But if you don't require an acceptance test for the material, you order it from the cheapest source, you may end up with badly heat treated material. And then if you go to weld it, you will do a very bad job on welding. Physically, it will look good. It will actually corrode very rapidly in service. One slide just about storage and handling. Most of us talk about stainless steels being handled properly, cleanliness, storage of material indoors, protected from contact with carbon steel, protected from surface damage, surface scrapes, dents, gouges, etc. It is even more important for nickel alloys and stainless steels. And you have to think of it as these are very expensive materials. Treat them very carefully, treat them differently than you do carbon steel or even stainless steels. So there are a lot of similarities between welding of the austenitic stainless steels and the nickel alloys. And in a way, the nickel alloys are all austenitic alloys, just like the 300 series stainless steel. So there's no need to preheat or post-weld heat treatment. Need for cleanliness, even greater for the nickel alloys. Reduced weld metal penetration, I'll come to that shortly. The weld pool is viscous. It doesn't move, it doesn't flow easily, and that is just a natural characteristic of the material that the welder has to live with. And we'll get into that shortly too. The thermal expansion coefficient of nickel alloys is less than 304, so slightly higher than carbon steel. So distortion is no worse a problem on nickel alloys than it is on 304. You can treat them about the same, even though actually the thermal expansion coefficient is less there. When it comes to weld joint design, we understand that the higher the nickel content, the less weld penetration you are going to get. That's a natural characteristic of the material. I'm showing a mild steel here run at this, and then 304, the same current amperage, and you get less depth of penetration there. And then an Inconel 600, which has 60% nickel, that's even lower penetration. So if the welder were just to look at it, he's going to try to compensate for that by turning up the current on the machine, and that's a bad idea. That's not going to help. You need to modify the joint design. So just like stainless steels, it's a matter of opening up the bevel, making sure that there's a wider root opening in the base if you're just welding from one side, and a smaller root face. And that's true for the high alloyed stainless steels and the nickel alloys. Now, for machine joints are preferred on thicker plates to hand grinding. Grinding any, whether it's stainless steel or nickel alloys, is not a great job. It's hard to do it, hard to control it, so you get a uniform joint preparation. For the welder's sake, because these are expensive materials and a little more tricky to weld, you really should have as uniform a weld joint as possible, and that's often done through machining of the material rather than hand grinding. So we mentioned that preheating is not normally required, but in environments where there's high humidity and you want to remove any moisture contamination on there, and sometimes people will take an oxyacetylene torch and just warm up the material so that it's warmer than the ambient air temperature, and you have no condensation on the material. Typical heat inputs for most of the nickel alloys are lower than the standard 300 series stainless steels, more like the 6% molybdenum stainless steels. The nickel alloys are fully austenitic. The filler metals are fully austenitic, and hot cracking can result if you have too high heat inputs. And we'll come back to that shortly when we talk about processes too. The interpass temperature, some people say 175 Celsius as an interpass temperature for most alloys. Others are conservative and say 90 degrees C. And I've always favored, if you say 175, the welder, chances are he's going to say, well, that's close enough, I don't need to worry about it, and maybe it's 250. So we usually like to say 90 or 100 degrees C maximum interpass temperature. Cleaning, we said, is important, and sulfur carbon can reduce both the corrosion resistance if they're in the weld joint or beside the weld. Low melting point metals from marking crayons, lead, zinc, etc., left on the surface, they can cause cracking. And contact with galvanized steel is another example of that. And the picture is a very famous one. It's probably about 60 years old now, but it is one of a alloy 200 which had sulfur contamination on the surface prior to welding, and it caused cracking. The sulfur goes along the grain boundaries and just spreads like crazy, almost like it is a liquid metal embrittlement situation there. But anyhow, it's very serious. So cleanliness is very important for all the nickel alloys. When we come to welding processes, many of the same processes used on austenitic stainless steel are suitable for nickel alloys. Gas tungsten arc welding or TIG welding is commonly used, especially for root passes. The shielding gas is pure argon, usually for manual welding. The backing gas would also be normally pure argon. Argon helium is used for automatic welding, where you can get higher speeds and in a consistent manner. Most often, TIG welding is done with filler metal. You really would like to ensure you're adding filler metal there. course, if you have very thin material, that may not be possible. And but any sort of thicker material, we would really like to have filler metal added for corrosion resistance and for hot cracking resistance. Presence of oxygen, carbon dioxide, and nitrogen and moisture can cause porosity, especially in the non-chromium containing alloys. We'll come back to that in a minute when we look at the copper nickel alloys too, but even keep it as low as possible for the chromium containing alloys. And if you have porosity, you see porosity in a weld, look for sources of oxygen or carbon dioxide or nitrogen or moisture in the welding process. Shielded metal arc welding or stick welding is widely used, and there are many different filler metals that are readily available. The nickel alloy 200 and nickel copper alloy 400 do require welder skill, as the molten pool is very viscous. This is especially important in shielded metal arc welding versus, for example, TIG welding or even MIG welding. So you can't expect the welds to look as good as they do on, let's say, a stainless steel with stick welding. Still acceptable, but they're not as good appearance-wise. Gas metal arc welding is commonly used when you have a lot of many meters of welds to do. It does take sometimes longer time to find the correct parameters for many of the nickel alloys. So there's a lot of setup time, a lot of practice time. That all costs money to do. But if you have a big job to do, it's the way to go. Submerged arc welding, it is used, but not commonly used. It's a high heat input process. You really have to run it at a relatively low heat input for it to work. And for most of the alloys, it requires very special fluxes, and the special fluxes are expensive. A lot of people don't want to buy the expensive fluxes. They use a standard flux that's used for stainless steel, and then they run into hot cracking problems. And in the end, it would have been much better for them to buy the expensive flux and get it right the first time. Flux cored arc welding and metal core arc welding, there's limited availability of filler metals. There are some quality issues still with it. They tend to be very expensive, but it's being developed now, and they are getting better. And they're especially useful where you want to use gas metal arc welding, but because of light windy conditions or other reasons where you're welding outdoors, they can be a good way of doing it to ensure a good quality weld. I'm going to get now more into some specific alloys and specific conditions here. I'm not going to talk a lot about the high temperature alloys. I just have one slide about it. They're used because of their high temperature strength and their resistance to the environment. It can be different environments, and different alloys are used in when it's oxidation versus carburization or nitridation or sulfidation. All that needs to be considered when selecting the filler metal. You want filler metals to have the right strength at the high temperature. You want them to have the right resistance to the environment. And one of the things that is different with high temperature alloys, whether it's stainless or nickel alloys, is the properties, the metallurgical structure of the material can change with time. And most often that means they embrittle with time. Now they take a much longer time to embrittle, but if you have a material that's been in service for 5 years, it might be quite brittle. They embrittle because of intermetallic phases, but also the grain size will grow. And when you have large grain sizes, all the impurities in the material go to the grain boundaries, and it makes it very easy for the grain boundaries when under high stresses to separate. And so sometimes repair welding, well, is very challenging, and sometimes it is impossible. And such a webinar on doing the high temperature alloys is really the subject of a separate webinar. Okay, so when we talk about the corrosion resistant alloys, we typically break them for convenience and for welding purposes only into 3 groups. The A group is the nickel and nickel copper alloys, and I will talk about the copper nickel alloys with that group too. The chromium bearing ones all have a certain similarity. We call them group B, and then the nickel molybdenum B alloys are the group C. And this only relates, I have to emphasize, for welding discussions. It doesn't relate to corrosion resistance. There's huge differences in the corrosion resistance within the same group. So when we talk about the commercially pure nickel, when it comes to the base metal, there are 2 different types. There's the 200 alloy, which has a relatively high carbon content, and the 201 that has a low carbon content. And the 201 base metal is used where you have a service that goes above 315 degrees C, because the carbon will get together and form essentially graphite at the grain boundaries, and then that's a problem with end use. It corrodes rapidly there. However, the filler metals are not subject to graphitization, so there's really only one type of filler metal used for both 200 and 201. The carbon in the nickel alloy is there to give it a little bit higher strength. We saw earlier it's a very weak alloy. Trying to get a little higher strength out of it, typically it will have a higher carbon level. The AWS classifications for the stick electrode and bare wire are given there. And as I noted before, the welders will note a very sluggish nature. The weld metal, it takes time to weld. You got to do it slowly to get a half decent appearance on it. The other major group A alloy is the nickel copper alloy, the Manel 400 type, and it's a little more welder friendly than commercially pure nickel alloy, and it welds reasonably well with in the bare wire, not so well with the coated electrode, but they've improved that a fair amount too. Now, the matching filler metal, E nickel copper 7 or ER nickel copper 7, is available, and you might think that's the one that is used, but in salt or brine environments, the matching filler metals may be anodic to the base material, and you might suffer galvanic corrosion. And those of you who know a little bit about galvanic corrosion, the worst possible case is to have a small area of material that's anodic, that corrodes preferentially to the larger area of cathodic material, the material that doesn't. And when you have a weld on a piece, that is the small area, so you definitely don't want to do that. Typically, there are 2 filler metals listed there. The second one is the 625 type filler metal, nickel chrome moly 3, and it is often used for welding the Manel 400 type materials in salt or brine environments. I'm now going to move on to the copper nickel alloys, because that was specifically requested, and they are somewhat different than even the nickel copper alloy, the Manel 400. The copper nickel alloys have a thermal expansion rate closer to 304, so they're higher than most of the nickel alloys, and therefore they're more prone to distortion than than the nickel alloys. So you want to keep the number of tacks to keep it straight, should be what you might use on a 304 material. And of course, it's very important to clean the tack welds of any surface oxide or any other contamination there after you have done the tacking. Most of the copper alloys do have, can imagine, have a higher thermal conductivity. They suck away the heat better. The 9010 copper nickel has a thermal conductivity maybe 4.5 times that of 304. So you have to be aware of that. The weld metal will cool faster than it would on a stainless steel. For the 7030 copper nickel, it's 2 times that of 304. And almost identical to the alloy 400 there. So still better than stainless steel, but not as good as the 9010. So again, the weld pool will cool faster than with the stainless steel, but not as fast as the 9010. And it should be noted for that interesting fact that I hadn't noted before was that carbon steel has a higher thermal conductivity than the 7030 copper nickel. It also sucks away the heat from the weld zone. Like the nickel alloys and stainless steels, no preheat or post-weld heat treatment is needed. Cleanliness is very, very important for the copper and nickel alloys. And that includes the filler metals too. So often if you have TIG wire sitting out in the shop, a lot of shops will say that you should take some solvent and wipe down the TIG metal or TIG rod before you start welding on the individual piece. And tools that you work with should be marked for use on copper nickel alloys only. So if you have a tool that's used on stainless steel previously, you can use it on copper nickel alloys, but then once it's used on copper nickel alloys, you don't want to use it on stainless steel. Copper is a bad actor on a lot of the stainless steels. So the best way of doing it is have the tools marked for use with copper nickel alloys only. So the 9010 filler metals, there are some available on the market. They're not actually ones that are normally used. There is, for example, no AWS specification for a matching 9010 filler metal. So most 9010 and 7030 are welded with a 7030 type filler metal, or occasionally, and we'll come into that the next slide, with the Manel type, the nickel copper filler metal. Now, these filler metals contain a small amount of titanium to react with oxygen and nitrogen to prevent porosity. However, titanium does, in the filler metal, does make, especially with the stick electrode, makes welding more difficult or ugly or whatever we want to call it there. So there was a question right at the beginning about titanium in these materials, that sometimes there isn't enough and you're getting porosity, and so it's a bit of a problem. You don't want too much in there because you get really ugly welds, but you don't want too little in it or you get porosity. So the basic option is to make sure that you have very clean materials, both base metals and filler metals, and make sure there's no moisture on there, and that the argon that you might use in a TIG torch is pure and is flowing at the right velocity, not too high, not too low, so you don't get oxygen in the shielding gas. The 7030 matching filler metal is in a different AWS spec than the nickel alloys. It's 5.6 for shielded metal arc welding and 5.7 for bare wire. And as we talked earlier, the nickel copper filler metal is in the nickel alloy specs. So TIG welding, use filler metal wherever possible. I mean, obviously, if you're dealing with 1 millimeter thick material, it may not be easy to use filler metal, may not be required, but in most cases, use filler metal, pure argon. Some people will add a little bit of hydrogen to the shielding gas. Again, the hydrogen is there to take out any oxygen or carbon dioxide, which might break down during the welding in the arc there. So some people will add a little bit of hydrogen. That's not a problem for the copper nickel alloys to do that. You don't want to use it in a lot of other materials, but okay for the copper nickel alloys. Use a short arc and a gas lens. I mean, most people are familiar with a gas lens, and that's just a little screen that's on the TIG torch that also called a diffuser, that causes the gas to not be as turbulent as it would be without that. Shielded metal arc, it's important to remove all slag between the passes, avoid start-stop defects, and if they occur, grind them out, re-weld if necessary. And in general, welds will not be smooth. And I just show a picture there of a shielded metal arc weld. It's a little bit hard to see. It's actually a boat being welded. I believe it's 9010. And you can see it is a bit rough. I'll say ropey is the term that we would use there. That's just a natural characteristic. There's nothing you can do about it. In seawater, once you remove any entrapped slag, that's not a problem in terms of the corrosion resistance. Okay. Gas metal arc welding of the copper nickel alloys, all three processes are possible. Typically argon or argon helium gas mixtures are used. When it comes to clad material, because copper nickel alloys are fairly soft, a lot of the times you're cladding it, you're either putting sheet on carbon steel or you have an integrally clad material, whether explosive clad or roll clad. Special welding conditions have to be done because the copper alloys, high copper alloys, have a very low solubility for iron. So if you get some contamination of the carbon steel into a copper nickel weld, you have problems there. So you have to make sure that you are not getting carbon steel into the weld where you're using the copper nickel filler metal. And sometimes the nickel copper filler metals, the nickel has a much higher solubility for iron, are used in that joint where you're attaching the two together, where you will get carbon steel pickup there. Just one final consideration about copper nickel alloys. Copper nickel is used to avoid fouling. The marine organisms attach themselves onto the piece. Copper is a poison to the marine organisms, so they don't adhere, or they don't adhere tightly to the metal. The higher the copper content, the more fouling resistant the material be. In general, we found that the 7030 copper nickel is very good, not as good as the 9010. So when you do a weld with the 7030 copper nickel, it is still quite resistant to this fouling. But if you use the nickel copper alloy, which has only 30% copper in it, it is less resistant. So you will get the marine organisms attaching themselves. So really, when you're using it in seawater, live seawater like this, you want to avoid having that nickel copper alloy, the 400 alloy, as the final weld pass seeing the seawater. So moving on, or getting back to the nickel alloys and the group B ones, the nickel chrome iron 800 is a common alloy. Now it is used both for corrosion resistant services and high temperature. So when it's corrosion resistant, you typically use a nickel chrome iron 2 or nickel nickel chrome 3 filler metal there. If you want a little bit higher strength, you can use one that contains some cobalt and molybdenum. Their high temperature service is sometimes very tricky because it depends on how it's used in the high temperature. There's different variations of the grade 800H, 800HT, but most often the filler metals used are the same as for alloy 600, which is the next slide here. The 600 is the shielded metal arc is nickel chrome iron 3, and the bare wire is ER nickel chrome 3. And they are high nickel filler metals. Now, there are a lot of other variations, 601, 602, CA, and all those are so different from the 600. They do require special filler metals and for high temperature service. And so I'm not getting into that here. I'm only really concentrating on the corrosion resisting alloys. So when we come into the nickel chrome molybdenum and the nickel chrome iron molybdenum, which are like the 625, 825 C type alloys, there is a lot of different variations of them. So if you think of the 6 molybdenum stainless steels, the 254 SMO, AL6XN materials, you're really worried about the microsegregation of molybdenum, which is why they are welded with a high nickel filler metal. Well, when we get to the high nickel alloys, such as 625 and the C alloys, that's not a problem, not a major problem anyhow. And typically we do use more matching filler metals. The exception to that is the 825, which is almost always welded with a 625 filler metal. There is a matching 825 one, but it is not commonly used. It's more used where you know that there's a problem with high nickel. And there are a few cases in fuel cells and things like that where high nickel can be a problem. If we move into the ones that are more commonly used in the chemical industry, the C-type alloys, here I'm showing the chrome and molybdenum, the major alloying contents other than nickel rather here. And the 625 had 9% molybdenum in it. That has a fair amount of corrosion resistance. The C alloys typically either have higher chromium or molybdenum. So the C22, 622 alloy has 4% more molybdenum than 625, so far more corrosion resistance. The older C276 had a lower chromium content, but really high molybdenum content, so it's used in strongly reducing conditions. And then the other C-type alloys like 59, the VDM version, 686 special metals, and 2000, a newer Haynes one, has both the high chromium and the high molybdenum. So you can just think that if you're welding 625, you can easily use from a corrosion point of view a C22 or a 622 filler metal there strictly for corrosion resistance. Now, it's a bit complicated because 625 is also used for high temperature applications, and there, of course, it's a completely different situation. But so let's say you have a C22 base material, you can weld it with the matching one, the C22 or 622, or you can go to a 59, 686, 2000 type filler metal because you know that the molybdenum content is higher and the chromium content may or may not be higher, but it's more corrosion resistance. So typically it is on the C family alloys, you weld it with a slightly higher alloyed filler metal to ensure that the weld is at corrosion resistance as the base metal there. But you do have a lot of choices, and they all fall into the same P group for ASME, but and they all behave somewhat similarly in weldability. Also, the base material, but even the filler metals. C276 can be a little bit rougher, but than the C22 or the 686. The final group is the group C alloys, which are the nickel molybdenum B alloys there. And the two common alloys are B2 and B3. B2, they've done a controlled chemistry version of it, which all the major producers follow these days. Maybe not all the producers in the world of the alloy. There aren't all that many, to be honest. And so the original earlier B2 version had problems that the B2 controlled chemistry has overcome. There are different filler metals available, the B3 and B4. B4 was a version that was made by VDM to get around the Haynes patent on their B3, but they've stopped making B4 now and are only making B3. I'm not sure about the availability of the B4 filler metal now. I know the wrought material, the plate, is not available now. Some of us love phase diagrams here, and this really just shows that the B2 alloy, you can get some brittle nickel molybdenum phases occurring in relatively short times, 6 minutes. Hopefully, during most welding operations, you won't be getting 6 minutes at 750 degrees C, but it is something to consider if you're doing any heat treatment on it, or if you're need to do a lot of repair welding on it, where the B3 alloy takes much longer time to form these phases. So really impossible to form during welding. I don't want to talk a lot about dissimilar metal welds, but often there are multiple choices of filler metals available that you can use for them. You have to really look at what the two different metals are, what the tolerance for the metals are. We saw that with the copper, high copper alloys, they didn't have a tolerance for iron. Some of like the B alloy with the high molybdenum doesn't have a tolerance for other things. So you really have to look at the particular combination. In general, they are relatively easy to weld with each other. And you really do want to use a filler metal there, because the filler metal is that combination of part base material, part of each of the base materials, maybe 15% of each, and then the rest is the filler metal composition. And for consistent quality, you do want to add a consistent amount of filler metal. So that's a welder skill that he has to learn, but it also involves doing the setup, the joint prep, and that sort of thing, so that it is all controlled carefully. And often the shielded metal arch is the preferred process for dissimilar metal welds, only because the welder can easily control the parameters there. TIG welding, it is difficult to use that. Just a few words on post-fabrication inspection and cleaning. As we can imagine, with anything that's being used in severe corrosion services, you do have to look and inspect the welds carefully for any kind of defects, which may impair its function in service. They're the regular ones. Even more important than with stainless steels, to look for these and find these and correct these, because of the severe service they're going into. And this also applies to high temperature services also. In high temperature, things get heated up and they expand, and then they contract as they cool down and heat up and expand again. So any type of surface defect can easily lead to cracking. Now, one of the questions that comes up regularly is, because of high alloying content, do we need to pickle the heat tint from the welds? And the laboratory scientific answer is that no, you do not, because the services that most of these are going into will actually dissolve any heat tint, any chromium depleted zone beneath the heat tint. So often they're removed only by a mechanical means, a stainless steel wire brush. However, because the equipment is expensive, your fabricator, your customer is paying a lot of money for this equipment, and they want to have it really look good. You want it to look good. So often they will put the pickling paste on the welds, and that does pickle away the heat tint. However, it really doesn't pickle the material underneath. Like with stainless steels, it will actually remove, pickling paste will remove a layer of stainless steel. A few atoms worth of stainless steel doesn't actually do it with these chrome nickel moly alloys, the C alloys, but it makes it look good and more uniform in appearance. So in summary, these fabrication processes can reduce the corrosion resistance of nickel alloys. We didn't talk about other things like forming, but that has an issue in itself. But it's important to know how to avoid the problems, because these are used in severe corrosion or high temperature services. You want to ensure the quality weldments are there, and that's a team effort with the welding engineer, even with the purchasing, your purchasing agent who buys the material. It's important that everybody get together and work as a team to ensure this. The filler metal will often be dependent on the service environment. You can't just say, okay, well, I'm always going to use this filler metal for this this base metal. It's not always working that way. The nickel alloys and copper nickel alloys are a diverse group of materials, important differences between the different families. And the most important step really is to prevent the problems in the first place, to do it right first. So we have a few publications that are available on our website free of charge. One is a newly revised guidelines for the welded fabrication of nickel alloys for corrosion resistant services. It's easiest to find on our website. If you use the number there, 11012, put that into the search engine, it will come right up. If you search on nickel alloys, you'll probably get 75 hits before you actually find the right one there, something we're working on. A brand new one we have also is, and it more relates to the use of copper alloys, the copper nickel alloys versus stainless steels for seawater cooling systems, written by Roger Francis out of the UK, a well-known expert in that area. We work together with the Copper Development Association on the copper nickel alloys. They have an excellent fabrication brochure available on our website as 12012. Again, that's the easiest way to find it. Also available on their website. And for the copper nickel alloys, there's a 5-part video series. They're about 10 minutes long each, on very practical aspects of welding copper nickel alloys there. And I give the, if you search for that, they're excellently done. Our welding expert, now retired, was part of the group that did the video series. And as Jörg mentioned, technical help is always available from our website, free of charge, and whatever the question is, it goes to the appropriate experts, and we have maybe 15 experts around the world, experts in different areas. So thank you. Now, I know there were some questions here.
Thanks, Gary. There's something about like 32 questions, 33 questions there on the Q&A section.
Yeah. How much time do we want to take, just so I know?
We can take another 15 minutes or 20 minutes if you want to answer a couple of them.
Okay, I will. I'll do that.
And we can email you the rest of the questions. If you can find time to reply to them, we can share it back with the guests.
Yeah. Okay. Good. Yeah.
In case some are not answered, then we will do that.
So what you just one of the questions was what grade of age hardenable alloy? Well, so we talked about the one for the Nickle 400 is called K500, but the 625 alloy has a number of different variations of age hardening. One and just on that 625, when it comes to weld overlays, 625 or the nickel chrome poly 3 filler metals are the most common ones used for weld overlays, but also there are and it's because the weldability is fine. But in terms of age hardenable, there's different trade names for them. I think Allegheny calls it 625 plus. I think Special Metals calls it 725. The 825 can come in an age hardening version they call 925, not very common, but so not all the nickel alloys have age hardening versions, but some of them do. Okay, let's see. Can you explain the need for nickel copper as barrier layer for copper nickel overlay? Okay. Yeah, well, the shielding gas typically is pure argon, but a lot of people, especially when you have a high humidity environment, they will use a little bit of hydrogen in there because it does any moisture that does disassociate in the arc will actually be taken away because it's the oxygen you're worried about there. So 70-30 copper nickel though is used if you want an overlay. If you're doing a weld overlay and you want the final pass to be 70-30 copper nickel, as the questioner says there, you use the nickel copper as a barrier layer, and it's because the 65% nickel that's in the nickel copper, the Nickle 400, let's call it, filler metal, has a much higher tolerance for iron. You do want to still make the amount of dilution as low as possible, even when you're using the nickel copper one. So you try to keep it around a 10% dilution if you can. But it's because the nickel has the high solubility for iron, which copper does not. Okay. There's a question about post-weld heat treatment. If you do a copper nickel overlay, and I will have to look into that because that is not commonly done. But I know from when you do nickel alloys like that, it's a tricky situation because any sort of post-weld heat treatment to stress relieve the carbon steel will often cause problems to the nickel alloy, and probably not the copper nickel alloy, but I want to look on that, and especially the alloy 400 overlay. But generally, they don't have a problem with intermetallic phase formation, so it probably is okay, but I would like to look into that. Yeah, okay. So the question about, and it's a high temperature one, about Incaloy 800H after heat treatment, they found a crack. We call that stress relaxation cracking. I will have to send the inquirer. there's a lot of work being done on that, on how to resolve it. I know this MTI organization that I am involved with, they have a project on that. There are things you can do, but it's not as simple as it might seem. So I'll delay on that. Okay. Yeah, okay, and I'll send some parameters in some of the brochures there. There is about shielding gas for the 70-30 copper nickel and volts and amps in there. That's in the brochure. The recommended flux core arc welding process for nickel alloy welding. I would say it's getting better. I'd hate to be the expert on there. It's probably not the first choice in fabrication in shop, but some of the and I would say especially the metal core ones, some of the alloys, they're not readily available as filler metals in bare wire. And because to make a heat of bare wire, you need 20 tons in the heat, and therefore you have to sell 20 tons of bare wire. You can make flux cord and metal cord materials in smaller batches, just like you can shielded metal arc electrodes in smaller batches. So sometimes you use it because that is the process or the filler metal that is available. And certainly when you're doing outside work or different environments where you can't control the cleanliness, flux core can be a good solution there. Guide on welding of explosion bonded nickel 200 plates to 5/16/70 pressure vessel steel. I have an answer to that in a couple of slides, which I'll send to the Inquirer. But you can the nickel 200 filler metals have the tolerance for iron. That's not a problem. The question is with the chemical process that the nickel 200 is used in. It's usually a caustic sodium hydroxide at very high temperature. And the question really gets back to how much iron can be tolerated in that final weld pass that sees the environment. How much the chemical company says you need it. In some cases, you can have 10% iron in there. That's not a problem. Most filler metals already have 5% iron or that typical amount in them. So the question always becomes what does the end customer allow there? And sometimes the end customer is something unreasonable, to be honest. So sometimes a discussion has to take place there. Difference between Inconel and Incalloy, those are trade names. So typically the Incalloy is the grades that contain a higher amount of iron. So Incalloy 800, Incalloy 825, those all have 20, 30, maybe 40% iron in them. The Inconel ones have much less iron in them. It's a bit of an arbitrary distinction, but those are trade names from what is now called special metals. Okay. While welding 825, which consumable is most suitable? So most people use the nickel chrome moly 3 ER or E nickel chrome moly 3 to weld 825. The 825 has molybdenum in there. You really want to have a grade with molybdenum. It's used almost exclusively where you have a corrosion issue, whether it's in the oil and gas industry, where it's hydrogen sulfide and chloride, or sulfuric acid, where molybdenum is beneficial. The E-nickel chrome moly 3, or the 625 type, is generally the most economical of those filler metals compared to, let's say, a C alloy. They have often the nicest weldability to them, so they are often used there for welding the 825. There's some questions about 800H and 800HT, and there are the differences. These are high temperature alloys, and it almost sounds like we need to do a webinar on particularly the high temperature ones here too. But basically, they're more controlled chemistry, and grain size is controlled on it also. So there are small differences in them, and some of the grades you can dual grade it, like 800 and 800H you can dual grade, or 800HT you cannot, because there are some particular restrictions on that. Problems faced in TIG welding of Manel alloys. The 400 alloy is fairly easy to weld. It welds reasonably well, and you really shouldn't have a huge problem with it. Cleanliness is important, and proper shielding is important with them. It won't look as nice as, let's say, a stainless steel alloy being TIG welded, but it should look still quite good. It's not too rough. Let's see. Copper nickel welding. If grain size of base metal is larger, then is it easy to weld? Well, it's you don't want large grains in copper nickel, and so just a bit of metallurgy on that. With stainless steel, if you heat it up to a certain temperature, the grains will reform, and so it's easy to get small grains on stainless steel. Same thing with 800H. If you need small grains, and small grains are not always good in the high temperature alloys, but it is possible to get them. With the copper nickel alloys, with pure nickel, it is not possible to get that. So if it's got a lot of high temperature application, the grains grow, and then it makes it sensitive to weld metal, or weld the grain boundary separation there. So so you don't want a large size, but it's also one of those things that's very hard to control, and especially in very thick material. Use reformer parts be welded without cracking? Another high temperature issue. And the question is, it depends on the alloy, it depends on the service. Some of the parts, reformer tubes, you actually have to do a heat treatment on it for 24 hours at a high temperature to actually redissolve all the bad embrittling phases that have formed. Other times there's not enough embrittling phases. You can use a certain filler metal that is fairly ductile. Again, we can talk about that at another webinar. Oops. Okay, just bear with me. Filler metal for joining. Okay. 25 chrome, 14 tungsten. Ooh, I'll have to look that one up. Recommendation for joining clad 316L with clad 625. the 620, it may sound like a repeating here, but 625 filler metal, the nickel chrome 3 filler metal, is really such a joy to use because it is so versatile. So to join a 316L clad with a 625 clad material, or solid 625 for that matter, yeah, use the nickel chrome moly 3. They're doing, the question involves doing a corrosion test, and it's really hard to do corrosion tests on clad material. And in fact, you want to, 625 is, I call it a very forgiving alloy. You can abuse it a bit more than a lot of the other nickel alloys. So it is possible to do a corrosion test on the base material that is clad by only doing, you use a rubber gasket around there and you do a corrosion test on it. So it is possible to do it, but to do it on the weld joint would be very, very difficult. And I don't see any reason for doing it either, to be honest. What's the reason behind lesser penetration for nickel alloys? I really don't know the answer to that, other than the fact that the high nickel alloys, there's probably a kinetic reaction happening, but I unfortunately don't know that. I'll leave that to the more academic people to figure that out. But it's a very good question, actually.
Thanks, Gary. I think you've taken many questions, and there are,
okay.
as you're answering, the number of questions are increasing. So we got, when you started, there were 35. Now I see 55. Yeah. So I guess I will send an email out to you. And if you could take your time to reply them, we can share with them. I see a lot of questions from one of our earlier specialists, Andy Sotevan from Andrew is online, I guess, and he's been asking a few interesting questions. So maybe I'll look forward to you answering them, and then I can share it with others. Sure. I believe Gary has shared his email ID, and we will share, with his permission, his email ID for others to ask questions if at all they want, so that they can always remain in touch with you. Yeah, and it can make it easier for you to answer further questions.
Yeah, absolutely.
Once again, take this opportunity to thank Gary and George for spending your early mornings and helping us out here. We had a strong 200 plus people attending all along. During the Q&A, we do see a slight dip, but we still have about 117 people there. So very well presented, Gary, and I believe a lot of people have benefited from it, and that reflects in the Q&A, because when people understand it, they want to know more, they keep asking questions. So thanks a lot. I will invite Mr. Malge to say the word of thanks, and while he does so, I will slightly do a little bit of promotion on the one-day training course we have. So I'll just project this on the screen while Mr. Malge extends his word of thanks.
Good evening, everyone. I'm extremely happy to propose word of thanks, Mr. Jog, for introducing the Nickel Institute and its activities to all the participants across the globe who are here. Then to Mr. Gary Coates for delivering a fantastic, educative, and very, very informative lecture, covering the entire the spectrum, starting from nickel refining to the end product and the quality. I really thank Mr. Gary for having taken so much initiative to formulate the particular presentation and put forward to the participants. And we had about more than 200 participants across the globe, and they stayed till completion of the talk, and that itself indicates that people are very much interested and they got benefit out of this. And I also thank our sponsors, Cotmac Industrial Trading Corporation Private Limited, who have